Okay, hello and welcome to the first ever stream on Probabilis. I am very excited to be here, and I'm excited to have you with me. So, let's discuss a little bit of things before we get started with the educational content. First, let me tell you a little bit about Probabilis. What is it? What can you expect from us? Stuff like that. So, Probabilis is both a YouTube channel and a Twitch channel. So at Probabilis, we are very passionate about education, and we want you to succeed in your school, whether that be through school tests, standardized tests like AP tests, SAT, stuff like that. We are here to help you, and it's completely free. We just want you to learn. So, a little bit about what you can expect from us. We'll be streaming every single week on Twitch with educational content. So we stream on Mondays, Wednesdays, and Thursdays. So on Mondays, you can expect Physics 1 content. On Wednesdays, you can expect calculus content. It'll mostly be focused on like BC calculus. And on Thursdays, we'll be doing Physics C content. So these will be happening every single week on those days. Additionally, we want to do bonus streams perhaps on the weekends, and those won't occur every single week, but they will occur every once in a while. And those streams will be dedicated for like SAT preparation, AP Lang preparation, AP Lit preparation, stuff like that. So that's our schedule, that's what you can expect from us. Additionally, we will be trying our best to post these streams on YouTube afterwards. So if you weren't able to join us live, you can still watch them afterwards and learn the content yourself. But if you're currently watching this on YouTube, you're welcome to come to our Twitch channel where we will be doing live content. This will give you the ability to ask questions in real time. We'll be able to see your questions in real time and answer to them immediately. And hopefully that'll tailor the learning experience better towards you, the viewers. So I think that's covered everything. I hope that's covered everything. Without further ado, today is Monday, which means we will be focusing on Physics 1. And since it's the first lesson, we'll be starting with the first unit of Physics 1, which is kinematics, and today we'll be focusing on kinematics in one direction. So let's get into it. All right, welcome. So we have some slides, and we'll be going through the content that you should have learned or you are currently learning in this subject. And then we have some practice problems at the end where I'll walk you through them. Hopefully you can learn some tips and tricks on how to approach these problems. And yeah, so let's do it. Kinematics in one direction, lesson 1. And at the bottom, there's a textbook reference where we referenced that textbook to get a lot of the information. So, physics, we don't usually need to know too many definitions, but when it comes to kinematics and when we're just starting out with physics, it's very important to know our definitions, because a lot of the stuff we do later on in the road in physics depends on this foundational understanding of some basic terminology. So let's go through these definitions. You want to become very familiar with these, and I'll just walk you through it, and we'll see what happens. So first and foremost, position. Position is a term that's actually kind of difficult to define, but essentially it's the location of an object relative to a reference frame, which is usually Earth. It does not always have to be Earth. For example, the position of my headphones are on top of my head. So, what's the reference frame in that context? Well, I said it's on top of my head. So the reference is my head because we're describing the location in terms of my head. So it's on top of my head. So it can be Earth. Maybe like the satellite is however many miles above the surface of the Earth, something like that. So what is position like that you might already be familiar with? Well, let's consider a Cartesian plane, which I'm sure you're familiar with, where you have x and y. And let's just take a random point there, which let's just say that's 3, 2. That point is technically a position. It is the position, but it has to have a reference frame. So in this case, the reference frame is the origin. Why is that? Because how do we get to 3, 2? We start at the origin, and we go over 3, and then we go up 2. And that works for any point on the plane. Here, this one, -4, -1, you do the same thing. The reference point is the origin. So there always has to be a reference point, reference frame. So that's position. Next is displacement. Displacement is defined to be the change in position. And this means that we have to compare the endpoints of some object moving, changing its position. And the units for this are meters. So we'll be using meters almost always in physics. It's the proper unit, the SI unit. And note that displacement is different from distance. And I'll cover this shortly, and we'll see it in the next slide as well. But let's just say there's this object here, it's a ball, right? And that's where it starts. And let's just say that we have to have a reference point, so let's just say this is x = 0. And let's just say this ball goes on some sort of journey and ends up here at this x. So, what is displacement and what is distance? So, for displacement, what we do is we compare the endpoints. So what are the endpoints? The endpoints, let me change colors here, are the starting point and, well, the ending point. And the distance is the line that connects the points. So displacement is the measure of the red line. So red equals displacement. So let's just say that maybe it's equal to like 5 meters or something, just something out of the blue. I don't know. So then what's distance? Distance is the actual path traveled, the length of that path. So in this case, that's the wrong blue, but that's okay. In this case, the blue is the distance because it measures the path that is being traveled. You measure each little bit along this path, and, well, clearly in this case that's going to be larger than our displacement because we can see that the red line is probably going to be much shorter than the blue line if we extend it out and make it straight. So maybe in this case distance equals 10 meters or something. So we can sort of see how displacement and distance are different. Distance, it can be any sort of path. Displacement needs to be the distance from the start point to the end point along the straight line connecting them. Cool, so that's displacement. Next is velocity. And that's simply the rate of change of position with time. So as we just saw in this example here, we can have an object that changes its position. It's perfectly normal for that to happen. Everything moves, right? So velocity, what that does is it measures how the position is changing as time changes. And we'll define this a little bit better a little bit later, but it's just a good sense to have. So yeah, that's velocity. And then next is acceleration. Acceleration is defined to be the rate of change of velocity with time. So okay, this is getting a little confusing. We have position, which is just the placement of an object. We have velocity, which is the rate of the change of position with time. And then acceleration is somehow measuring that rate, how it's moving with time. So velocity, you might be able to understand that that has something to do with movement. It's somehow related to speed. Acceleration is a little bit harder to grasp visually. So for me, I really like to think about cars when I think of acceleration. When we're driving a car, we have the accelerator as one of the pedals. And what does that do? Well, that kind of makes you go faster, right? But we'll see that a little better a little bit later. So next, there's a couple of equations for velocity, speed, and acceleration. So the average velocity is the change in displacement with change in time. We sort of already defined that. and that is given by delta x divided by delta t. So we use x to signify the position of the object. So, so x is position. And then delta is the symbol for change. So essentially we're saying change in x, change in position, divided by change in time. And that makes sense because that's the formula for velocity. Next is average speed, which is the distance traveled divided by the change in time. So that's a little bit different because this is distance and this is displacement. So let's go to this example here, and I'll zoom in a little bit so it's a little easier to see. And let's just say that this journey took 5 seconds, right? Took 5 seconds. So if we go back here, velocity is the change in displacement divided by change in time. Speed is the distance traveled divided by change in time. So what would be the velocity for this? Well, let me change colors again. Velocity is equal to change in displacement, I'll just abbreviate it here, divided by change in time. And that is equal to, well, this quantity here, 5 meters divided by 5 seconds. And that is equal to 1 meter per second. So that's the velocity. Now, what is the speed? Well, I guess we don't need the question mark because we're going to figure it out right now. That is equal to the change in distance divided by change in time. Or alternatively, just the distance traveled divided by the change in time. So this, well, we know the denominator is still 5 seconds because that's how long the trip took. But this time the distance is 10 meters. So this means that the speed is 2 meters per second. And so a lot of students have, some difficulties understanding the difference between velocity and speed, but we'll clarify that in just a moment. But first, let's talk about average acceleration. That just follows similarly. That's the change in velocity divided by the change in time. So if we're given a starting velocity and ending velocity, we can compare the difference between them and divide that by the change in time. So if, say, here, the ball had a speed of 0 meters per second, and at the end point it had 4 meters per second as its velocity, then the acceleration equals change in velocity divided by change in time. So that would be 4 minus 0 divided by 5, because the ending velocity was 4, starting velocity was 0, divided by 5 total seconds. So that would be 0.8. Let me just add some units here. Meters per second. Let me just fix this up a little bit, make a little neater. Meters per second, right? Because that's velocity, and this is second. So this is equal to 0.8 meters per second, and another way of writing that is 0.8 meters per second squared. So those will be our units for acceleration. For speed, it will be meters per second, and velocity as well, sorry. I just underlined those backwards. But now comes the very important part, the difference between a vector and a scalar. So these are terms that are very important to know. So a vector is a quantity that has direction and magnitude. So that means that we have to specify some sort of value for vector quantities, probably some number, as well as some sort of direction. Where is that number being applied to? We'll see that in just a moment, but a scalar is a quantity that just has magnitude and no direction. So most of the times, that's just a number. So, of the things we've seen thus far, which are vectors and which are scalars? Well, position is a scalar. Why? Because, well, I guess it really depends. Here it can be, if you're just looking at the pure numbers, it can be a scalar. However, if we were to describe the position of an object in terms of the reference point, which we almost always do, we require it would be in terms of the vector. So position can go either way. I think most times you'll see it as a vector, sometimes it can be a scalar, but nothing to worry about there. Displacement is a scalar. Why? Because we're just taking the difference of two numbers, the positions, and as we saw, it's just like 5 meters, right? It's just a number. So that's just scalar. Velocity and acceleration are our important vectors. So these are the most important things. So for velocity, we have a number given. Let's see over here, 1 meter per second. And that's right here. However, we don't have a direction associated with it. This 1 meter per second could be anywhere. It could be 1 meter per second north, could be 1 meter per second east. We don't know. So in this case, the object is moving to the right. So we would specify this by saying 1 meters per second to the right. And this is a very vague description of like the direction in terms of velocity, like for the vector. Further down the road, you may have to express it in terms of math, like in coordinates and stuff like that. But for now, we have to specify to the right, because now we know where the object is traveling. All right. Acceleration, same thing. We have to know in which direction is the object getting faster or slower, in which direction is the object changing its velocity. So in this case, we have 0.8, which is a positive number, and oftentimes direction can be provided by its sign. If we have a positive number and we specify a positive direction, that would give us the direction of the vector. Similarly, if we define a negative direction and we have a negative vector value, that will describe the direction of it. But since we didn't describe which is the positive direction or not, here we would have to say 0.8 meters per second squared to the right. Alternatively, what we can do is we can go back to this example and just say that like this is the positive direction and this is the negative direction, and then we would see from our answers that like, okay, the positive direction is to the right. Great. So those are the definitions, and that's a lot of stuff to comprehend all at once. But hopefully as we do some more problems, stuff like that, we'll be able to get into the swing of things. I realize my picture may have been in the way at the bottom, so I'm just going to make it a little bit smaller, and hopefully that doesn't happen too much in the future. It's the first stream, I still have to get used to things. But let's move on to this next slide. So distance is a scalar quantity, whereas displacement is a vector quantity. And I think we just touched on this, but it makes sense, right? Displacement, you're comparing the endpoints, you're drawing a straight line between them. You have to specify in which way is that line being created. It could be going this way, it could be going that way, you know, we don't know. So like if we were just given the displacement as a number, 5 meters, like from A, our endpoint could be like here, right? We don't know that it's actually here. So the direction is very important. So we get the final displacement where the object actually is. However, distance is not a vector quantity. It doesn't need that direction because, well, like distance, it can go on any sort of path that it wants. It would be so hard to describe the direction of an object's travel throughout the entire path, right? It can go on literally any sort of path. Here, I'll draw a different one, right? Like, how are we supposed to describe that as a vector? It just doesn't make any sense. It's such a complicated path. But since displacement is a straight line, we need to make sure to specify it as a vector. All right, onwards. So I think this slide is really, really important. This describes relationships, and I think it's very helpful to understand these relationships, especially for graph problems. You'll see a lot of graph problems, especially on the AP Physics 1 exam. It's super important to know these immediately, not have to like recall what it is, just know these like the back of your hand, which, by the way, that saying doesn't make any sense because you don't really look at the back of your hand all that much. I don't know. Anyways, So I have this little chart here, and you'll see many different types of graphs throughout this course. But these are all graphs in relation to time. So we have position versus time, velocity versus time, acceleration versus time. And with those graphs, we can get some interesting quantities. So if we have a position versus time graph, and we take the slope of that line, we get velocity. If we take the area under the curve of that graph, we don't get anything that's useful to us. Next, if we look at a velocity versus time graph, and we take the slope, we'll get acceleration. So before I continue on, let's see if we can understand why this is the case. Velocity is the slope of a position versus time graph. What did we say velocity was? Velocity was the change in position divided by the change in time. And well, what is slope a measure of? Slope is the measure of a rate of change of something. We learned slope to be like y2 minus y1 divided by x2 minus x1. It's the change in the y coordinates divided by the change in the x coordinates, right? So when we have a position versus time graph, when we take the slope, we get velocity. And the same thing, the slope of velocity versus time is acceleration, because acceleration is a change of velocity as time progresses. Cool. However, if we have a velocity versus time graph, another thing we can do is take the area under the curve of that graph, and that gives us the displacement. And for that, we would need like a start point and end point to take the area under the curve, but we'll see a practice problem in just a few moments that, goes over area under the curve, stuff like that. And then acceleration versus time, if we take the area under the curve, we get velocity, so it's just sort of going backwards, like in this direction, whereas slope was going in this direction of what it tells you. Also, if you take the slope of an acceleration versus time graph, it gives you a quantity called jerk. We don't touch on jerk in this class. We don't even talk about it in like physics C or anything like that. It's just a fun fact to know. I learned it when I took physics 1 and I thought it was just a fun fact. So yeah, that is good. Memorize this. This will help you out so much when you see graph problems. It will be just amazing to have this down in your memory. All right, let's continue onwards. So now we'll pause for a moment to take a look at the difference between instantaneous and average velocity, and, well, constant velocity. So let's start with constant velocity. What do we think that means? If something is traveling with constant velocity, I sort of compared velocity to speed earlier on, saying that they're quite similar, and they are quite similar, except velocity is a vector quantity, so we have to describe direction. But we're also familiar how velocity was in meters per second, and we can see like how a car would travel in 30 meters per second, however fast that is. I can't do the conversion quick enough. So a constant velocity would be that car traveling at 30 meters per second at all time. It's not speeding up, it's not slowing down. So what would that look like in a position versus time graph? That's not a good. So let's just say, actually let's look at a velocity versus time graph first, right? So this is velocity, this is time. Well, if it's traveling at a constant velocity, it's going to be a constant line, right? It's traveling at 30 meters per second at all time. Well, that's given by a horizontal line. So now we have position versus time. What do we want to see? Well, we know that the slope of the position versus time graph should give us the velocity. And if the velocity is constant at all times, that means the slope of the line should be a constant at all times. And it's a constant positive number, so we want a positive slope. So it would look something like that. Because if we take the slope of that, say the slope of that is 30, then we should get a constant horizontal line here for velocity at 30. So that's what the graphs would look like. And what would the acceleration versus time graph look like? Well, what's the slope of a horizontal line? Rise over run, it rises 0, and runs a lot, but the slope of that is 0, so we wouldn't have anything for the acceleration versus time graph because, well, it's not accelerating. The velocity is constant. Makes sense. Instantaneous velocity. We won't spend too much time on this, but that's essentially saying, what is the velocity of an object at this point in time? What is the velocity at t equals 2.2 seconds? So that could be, well, could be anything, right? As long as, like, it's not faster than the speed of light or something like that. But, yeah, it could be anything. For a car moving, and if it's accelerating, it could be like 2 meters per second if it's just starting to move. Or if it's on the highway at like t equals 1 hour, maybe it's going at 40 meters per second. Actually, that seems quite fast, but just go with it. So instantaneous is at a specific time. The average velocity takes a specific point in time, but compares it to a starting point. And that's what we see in this graph here. We have the starting point A, and we're looking at these specific points in times B. And essentially what we're doing is we're given a position versus time graph, and we're calculating the slope, again, right? The slope of position versus time is velocity. So at these points B, we draw the line connecting them and calculating the slope of that, and that gives the average velocity in that time. What would the instantaneous velocity look like at point B? Well, this requires a little bit of calculus, so I won't talk about it too much, but it's essentially the slope of this curve at the point B. So we take like a tangent line and find the slope of that. You're not expected to know how to do that. Don't need to worry about that. That's more of a physics C concept. But it's still helpful to know these definitions: instantaneous, average, constant. Cool. And here we have this really cool picture. So the first picture, the top of the picture, is just a car moving at constant velocity. And we see how the arrows are all the same size, right? And the car's distance between like successive time steps is the same. And that's what we would expect, right? It's traveling at a constant speed, constant velocity, so the direction is the same throughout, right? It's going to the right every single time. Same magnitude of the velocity, stuff like that. So, just as we expect, nothing's really changing. It's not speeding up, it's not slowing down. So now we go to B. And instead of looking at the velocity, let's look at the acceleration. And for convenience, I will just define this to be the positive direction. So we see that the acceleration vectors are pointing in the positive direction. I don't know if that's going in the right direction on the screen. Bear with me. Okay. So the acceleration vectors are pointing in the positive direction. So that means the object is accelerating in the positive direction. And well, what does that mean? That means that the velocity is changing with some positive amount. So that means that the object is getting faster and faster. And we see that in the picture, right? This velocity vector is really large, whereas we started out really small. And think about it. When you're in a car and you start at rest, you're at a stoplight, and then you or your parent steps on the accelerator when the light turns green, you start from rest and you start out slow, and then finally after some time you get back to the speed that you were originally at. So that's what the second picture is displaying, a positive acceleration. And now we have the third one. And again, I'll define this to be the positive direction. And we can see now the acceleration vectors are the same size, but they're pointing in the negative direction. So for this, we have to take a look at the starting velocity vector. Initially, the car is moving in the positive direction at a high velocity. That's why the arrow is so large. But the acceleration is slowing it down. It is pulling it. That's how I like to think about it. Acceleration is a pull. Here, the acceleration was in the same direction as the direction of travel. So if we were to pull in the same direction, that object would be getting faster, right? You're pulling something in the direction it's going. Now, we have an object going this way at some speed, but we're counteracting it. The acceleration is pulling it this way. So in this sense, we can think of a car deaccelerating. Say you're driving on some road and you see a stoplight and you want to slow down. So you lift your foot off of the accelerator and you put on the brake, and your acceleration is pointed in the negative direction, and you slowly come to a stop. So these two are sort of opposites, but the thing that's different about them is the direction of the acceleration vector. So hopefully that's a helpful visual. You can sort of see how things are going on with that, and hopefully that helps. Cool. So now we're moving on to the fundamental forces. So these are just things that we kind of need to know, just as definitions. So it's just helpful to go over them. So the first bullet point is there are 4 fundamental forces. And these are the strong, weak, electromagnetic, and gravitational force. So briefly, the strong and the weak forces, that has to do with like atoms, how the neutrons and protons are interacting with each other within the nucleus of the atom. So we're not really concerned with that too much. It's quite complex. Electromagnetic, that has to do with electricity and magnetism. We'll see this more at the end of this course, at the end of Physics 1, when we explore electricity. So we'll save that for later. But we'll really focus our attention on the gravitational force. And we see that the root of that word is gravity, and I'm sure many of us are familiar with gravity. We'll talk about that shortly. But first, what are forces? Forces are things that influence the motion of an object. So I like to think of forces as a push or a pull. Now, I'm going to stop for a second. Before I said acceleration, you could think of it as a pull or a push. That does not mean that acceleration is a force. That was just a bad choice of words on my part, but it was a helpful way of thinking of what was going on. Forces are actually pushes or pulls. If I pull down on my headset, which I'm not going to do, I am applying a force to it. Gravity is actually a force. There is a gravitational force, which is literally right here. And that occurs when something falls down, right? Gravity points downwards, something's falling downwards, gravity is acting on that object, it's pulling it towards the ground. So that's literally a pull. So, just to clarify, acceleration is not a vector. Acceleration is a vector. Acceleration is not a force. Forces are pushes or pulls. Now, specifically, forces do influence the velocity of an object, and that makes sense, right? When we talked about the gravitational force, something falling down from the sky, the object will get faster the more that it falls, right? We see that. If you drop something from a tall building, it starts out kind of slow falling through the sky, but once it reaches the bottom, it's going pretty fast, right? So forces influence the velocity, and we'll explore that further in future units, I think, but it's just helpful to know for now. And importantly, force is a vector quantity, magnitude, direction, stuff like that. Gotta know that. And then we'll also be tossing around the term net force. So net means this full force, and essentially that just means the vector sum of all forces acting on a body. So an object need not have just one force applied to it. For example, I said if I pull down on my headset, I'm applying a force to it. I can, call someone else over and they can also pull down on my headset at the same time. We're both applying forces, so the net force would be the sum of those forces. The amount of force I'm applying plus the amount of force someone else is applying. Great. And as always, that causes a change in the motion, right? Force influences the velocity, change in motion. That should, make sense. And lastly, acceleration is proportional to the net force. I'll just speak very briefly about that. We will see an important equation, F equals ma, quite a bit later on, and we'll spend a lot of time on that because that's a very important physics equation. But essentially we see that this F is force, and A is acceleration, so they're directly related to each other. Cool. So that should cover that. Let's move on. And we're going to talk about this dude right here and his apple. There's a lot of, discussion about whether or not an apple really fell on his head, and I believe the consensus is that it never did fall on his head, but I've heard things about, he was near an apple tree and he saw an apple fall from the tree, and that's how Newton came up with his idea about gravity. I don't know the story. This was, centuries ago, so it doesn't matter too much. But what does matter is the theory he came up with, and it's super important. So, what did Newton really talk about? He talked about free fall amongst, a ton of other stuff. This guy was, a genius. But we will be focusing on free fall, which is something that he pioneered. And free fall is the term we use to describe an object that is falling in the sky. So, how do you draw an apple? No, we're not drawing an apple. We'll see that I'm a very bad artist. But yeah, let's just say we have an apple here, and it's falling in the sky, and, it's just going to the ground. It's experiencing free fall. And essentially that means that the only force acting on it is gravity. There's nothing else, it's the only force that's being applied on it. And for this course, we ignore air resistance and, other sorts of friction in the air for now. But if you decide to take Physics C, you will encounter air resistance, taking that into consideration when doing calculations. But for now, we're just saying the apple's falling from the sky. Hooray. Cool. So, Newton has defined the quantity acceleration due to gravity, which is a constant value. And we denote it with the lowercase g. And on Earth, g equals 9.8 meters per second squared. And notice the units are meters per second squared, and this is the acceleration due to gravity. You should remember a couple slides earlier, I said that the units for acceleration were meters per second squared. So that matches, which is good. And you might be familiar with this term, 9.8. You may have seen that before. It's a very common number in physics, and we'll be using it a ton in this course. But yeah, that is the acceleration due to gravity on Earth, and that just describes how an object's velocity changes as it's falling in the sky on Earth. And there's some other values for different planets. Mars is 3.72 meters per second squared. The Moon is 1.62 meters per second squared. Jupiter is 24.8 meters per second squared. So let's try to consider this, conceptually. If you've seen videos of Neil Armstrong, Buzz Aldrin, the other people who have went to the moon, we know that the astronauts sort of float when they jump. They jump and it takes them a really long time to land back to the ground. And that makes sense because there's such a small gravitational constant there. The velocity doesn't change as quickly as it does on Earth. And in fact, it takes about 1/6, it's 1/6 as small as the gravity here on Earth. So they do float a little bit, and it takes a little bit of time for them to land. On Mars, it's about a third of the value. So if humans go to Mars, I don't know what's the year they're supposed to go. Is it 2024, 2025? Sometime soon. I don't know what SpaceX and NASA are planning. But whenever that happens and we get video of it, which I'm sure we will, we'll see that they won't be able to walk the same way as they do on Earth. They won't be able to jump the same way on Earth. It'll be slightly different. Not as extravagant as on the moon, but it will be noticeable. So that's just something interesting to keep in mind. Jupiter is 2.5 times our gravity. So yeah, that would not be pleasant to live on. We would have some brain damage after quite a bit of time. Anyways, that's enough of that tangent, but I think it's just cool. I think it's fun stuff. Anyways, in freefall kinematics, the acceleration of the object is equal to g. And if the positive direction is upwards, then the acceleration is negative 9.8 meters per second squared. So why is this the case? Well, I said when an object is in freefall, the only force it's experiencing is gravity, right? And we have the gravitational constant, this 9.8 meters per second squared, and I briefly showed how force is related to acceleration, but that's not super important right now, so I'll cross that out. But the thing to note is that there is only one force being applied on it. Acceleration is linked to force, so in this case, acceleration equals the gravitational constant. Awesome. Let's move on. So these are the kinematic equations. These are super, super important to know. I highly recommend memorizing them. I'll admit, I did not memorize them immediately. And boy, can I tell you, that was just a struggle, because every single time I would have to flip back through my notes and figure out what were the equations again. So if you just remember the equations, there's just 3 of them. It'll help you so much. It'll save you so much time. So I won't read through these equations, but I'll just define a couple of the terms. So if we see v is velocity, so v naught is initial velocity. So that's self-explanatory. It's the starting velocity. Vf, as you might be able to guess, is final velocity. A is acceleration. And t is time. X, f, and x0, well, we should remember that x denoted position, so this is final position. And x naught is initial position. So those are the equations. Again, please memorize them. It'll save you so much time. I'm speaking from experience here. You don't want to flip back and forth because these equations are used everywhere at all times. So yeah, we will be using these equations in some of the problems we look at. So before we do some problems, a couple of tips that I think will help make you succeed. First things first, decide on a direction. Directions are super important in physics. Why? Because, I've been mentioning vector quantities a lot, how vectors have to have both magnitude and direction. So instead of having to write out very specifically how the direction is pointed, like where the direction is pointed to, if we start out by saying that this is the positive direction, this is the negative direction, it'll save us a lot of time, and also we can adjust the signs of our variables to match the directions. So like I said, in free fall, if we say the positive direction is upwards, then the acceleration is negative 9.8 meters per second squared, because the object is going downwards. The acceleration is pulling it downwards. Next, write down all of the known variables and circle the variables that is or are unknown. So this is purely an organizational thing. In 1D kinematics, we use these equations a lot, and usually in the problem, they'll give you some of these values on the right. And it really helps to write down those values immediately. So you can just say that, okay, Vf equals 5 meters per second. Maybe they tell you the final velocity is 5 meters per second. So yeah, I like to write them right away. And then I also like to note which variables I don't have yet. Next, you want to choose the kinematic equation that has all but one of the known variables. So most of these equations require 4 or 5 variables, and most of the time you'll be given one less than the known amount of variables. So suppose I'm given the initial and final position, the initial velocity, and acceleration. Well, that's this one, this one, this one, and this one, and I look at the equations, and I'm like, okay, I have this, I have this, I don't have this, and I don't have this. So the first equation is not going to work because there's 2 variables I don't know. Second equation, I have this, I have this, I have this, I don't have this, I have this, and I don't have this. But the time is the only thing I don't know. So for solving for time, we can use the second equation because there's just one unknown. So that's just what you would do. So you would choose the correct kinematic equation, make sure the last variable that you're trying to solve for is the unknown. Then you just substitute the values in and solve for the quantity that you need. Lastly, once you've solved the problem, you want to make sure the direction matches. If you're dealing with a vector and you have to specify a direction, make sure it matches the directions you specified as the positive and negative directions. And lastly, what's super important is, does the answer make sense? And this can be a really tough question to answer sometimes because some of the things we deal with are kind of abstract. It's hard to conceptualize how fast exactly 5 meters per second is. Sometimes we're given like really random values in the problem, like a car is traveling at 100 meters per second, that's given to you in the problem, but that's like insanely fast for a car. So your final answer might not be like normal for a car, but in the context of the problem, it makes sense. So use your intuition based off of what you know about the physical world and what you know about the variables that have been given to you already. All right, so we'll start with the first question. But first, I'm going to get a sip of water. We can look over this question, start to read it, and start to formulate any hypotheses about how to do the first few parts of it. Okay, so let's read this problem out loud. So, Kermit the Frog is chilling in a pond. He decides to hop on some lily pads. He jumps 3 lily pads to the left, then changes his mind and hops 2 lily pads to the right. His entire journey takes 10 seconds. So, before reading the individual parts, I like to sketch out pictures. Sometimes it really helps to visualize. I am more of a visual learner. It really helps me solve problems. Not everyone is visual, but for those who are, let's just look at it. So let's just say we have a bunch of lily pads here. Doesn't really matter how many. My artistic abilities are really shining right now. Anyways, so he starts on some lily pad. Let's just say he starts on this one. And yeah, that is totally a frog. And he decides to hop on some lily pads. So he jumps 3 to the left. So he goes 1, 2, 3. And then changes his mind and goes 2 lily pads to the right. 1, 2. So this is his final location. So I'll just put an F here. This is the initial location. Maybe I'll do that in a different color. Orange is cool. Orange, original and final location. Great. So we've drawn a picture. We sort of know what's going on. Cool. Part A. What is Kermit's displacement? So, displacement, that is the change in position. Change in position. So, what does that mean? Well, we have Kermit's starting location, and we have his ending location. And we have to compare the endpoints here to here, right? So, what is that displacement? Well, that's just 1 lily pad, right? There's only 1 lily pad that he has to jump to get from his initial location to his final location. We're just comparing the endpoints here. However, we must also specify a direction, because 1 lily pad could mean he goes to the right 1 lily pad, which is not correct. So we have to say 1 lily pad to the left. So that's displacement. Part B. What is the distance that Kermit traveled? Okay, so distance is different from displacement. Displacement compared the endpoints. Distance means the entire journey. It's measuring the entire journey. So he went 3 lily pads to the left. So distance, he went 3 to the left. I'll just put that in parentheses here. And then he went 2 to the right. So how will we combine this information together? We're measuring his total journey. Well, in total, he traveled 3 plus 2 lily pads. right? He traveled a total of 5 lily pads. And we don't have to specify a direction here because it's a distance. It's just measuring the journey. He went 1, 2, 3, 4, 5, right? We're just counting the journey. So we see the difference again between displacement and distance. C is the average velocity. So velocity is denoted with a V. Average is usually given with a bar above it, so that's average velocity. So that is given by the displacement, which is essentially delta x, divided by the change in time, which I'll just denote as delta t. Well, we already have the displacement, right? That's 1 lily pad, and for now we'll just focus on the magnitude of it. So 1 lily pad divided by, well, what's the time? We're given that the journey takes 10 seconds, so t equals 10 seconds. So we'll divide it by 10 seconds. And if we compute this, we get 0.1 lily pads per second. Cool, so that's velocity, but wait, it's not velocity. Velocity is a vector. It requires magnitude and direction. Right now, we have only specified magnitude. We have to specify a direction as well. And that's where this little specification comes in handy, right? The displacement was 1 lily pad to the left, so his final location was to the left. And so in this case, the velocity is 0.1 lily pads per second to the left. Alternatively, what we could have done is we could have started the problem by saying, let's let this be the positive direction and this be the negative direction, right? And then maybe let's just let this be x equals 0. So then his initial is x equals 0, and final is x equals negative 1. So then displacement, we can see the difference is 1. Distance is the same calculation. It doesn't depend on initial and final. It's the journey. Velocity, that is equal to delta x divided by delta t. Actually, let's revisit delta x, which is displacement. So delta x is the final position minus the initial position. So that would be equal to negative 1 minus 0, which is negative 1. And we have the same number here, 1, but this time the negative is specifying the direction for us because we specified the negative direction right there. So that's where the sign of the number can come in handy to specify direction. Similarly here, when we're computing delta x divided by delta t, we would say that this is negative 1 divided by 10, which is equal to negative 0.1 meters per second. Not meters per second, but lily pads per second, which I'll just say LP per second. But we can see here, again, the negative is specifying the direction for us. Amazing. Let's move on to part D. So what is Kermit's average speed for the journey? So speed doesn't really have a variable associated with it. So I'll just say average speed. And that is equal to, well, what's that equal to? That's equal to the distance, not the displacement, the distance divided by change in time, the time that's elapsed. Well, we know the distance, that's 5 lily pads, so 5 LPs. And the time, we know that's 10 seconds. We don't have to worry about direction here because it's not a vector quantity. So we can just compute this, get a scalar value, and we get 0.5 lily pads per second. And that's our answer. So that's the first question. And that should cover like the first concepts we learned. Question 2. We have some true or falses, and then we'll analyze this arrow drawing. But we kind of already did that, so we'll see. True or false? An object can have constant speed and a non-zero acceleration. So let's think about this a little bit. Constant speed, we're pretty familiar with what the term speed is. You know, we just think about cars and vehicles and how they move, stuff like that. I'm just gonna adjust my camera a little bit so that way it's, I'm not cutting out all the time. Anyways, so an object that's moving at a constant speed and a non-zero acceleration, which means the acceleration is either positive or negative. But doesn't acceleration mean, like, that's the change in velocity divided by the change in time, and velocity is related to speed, so we would sort of expect that to not be possible, right? Because it shouldn't be traveling at a constant speed, it should be changing. However, unfortunately, I hit you with a tricky question. This is a trick question, and the answer is true. And why is this true? Well, we will see this in a future unit, but essentially, we can have an object traveling in a circle. And essentially what's going on here is that as the object is traveling in a circle, the magnitude of its speed can stay the same, right? We can have the same speed, you're just driving in a circle, right? But the velocity is changing because the direction is changing. At this point here, the velocity vector is pointing that way, right? You're going in this direction, sort of. But at a completely different point, you're going in a different direction. So even though you have the same speed, the same magnitude of velocity, your velocity can still be changing, which means acceleration is non-zero, because acceleration is measuring a change in velocity. So there is a change occurring, which means there is acceleration. So this one is true, kind of tricky. B, true or false, an object can have constant velocity and a non-zero acceleration. So this one, okay, now we might be thinking, all right, this is maybe the one that's false, right? Speed, all right, they tricked us, you know, that doesn't have a direction. We didn't really think about direction. But now we should be pretty sure that this is false. And we would be correct in saying so. And why is that? Acceleration equals the change in velocity divided by the change in time. If the velocity is constant, then this tells us the change in velocity over some period of time is equal to 0. And that implies that acceleration is equal to 0 divided by change in time, which is 0, and that's not non-zero. So B is false, A is tricky, sorry about that, but it's a good lesson to learn there. It just shows the good difference between vectors and scalars. Part C, describe the velocity and acceleration of the following motion arrows. I won't spend too much time in this because we kind of did something similar, but this is the positive direction, that's the negative direction. Let's just look at part A. So the object's moving with a positive velocity because it's moving in the positive direction, and it seems that the velocity is getting larger, right? The lines are getting longer, so the object's probably moving quite fast. So that means the object was speeding up in that time, so the acceleration was also positive. So I'll just say V is positive, acceleration is positive. B, the velocity is positive still because the object's moving in the positive direction. So that should be pretty easy. This time the object is slowing down, so you can think about like my example, if you approach a red light, you see a red light, you slow down and you take your foot off of the accelerator. So acceleration is actually in the negative direction because, I hate to use the word, but think about how it's pulling you back. It's stopping you. It's preventing your movement. It wants you to move in the other direction, but you're already moving in the positive direction. That's the best way of thinking about it. C, the lines are all the same. So the velocity is constant, right? There's not really a change in the velocity at all because the arrows are all the same. And it's still positive because we're going in the positive direction. So if the velocity is constant, what does that tell us about the acceleration? Well, we just showed it up here. When the velocity is constant, acceleration is 0. So that one was pretty easy. Part D, velocity is negative. That should be pretty easy to see. Arrows are pointing in the negative direction. Its velocity is negative. However, this is a little bit annoying, but sorry, that's the next question. Oh no. In these three examples, the starting point was sort of on the left, right? It was going in towards the right. But now, since the velocity is negative, we're actually starting at this rightmost point and then going towards the left. So we can see that the object's velocity, the magnitude of the velocity, is actually getting quite a bit larger because the arrows are getting larger the more you go to the left. So the acceleration is, it's negative. It's in the negative direction, but the object is speeding up. So an object can be speeding up even with negative acceleration. And that just comes down to the direction. Since the velocity was in the negative direction, and acceleration's in the negative direction, the object actually speeds up. And lastly, velocity negative, arrows are pointing in that direction. This time, the acceleration is positive. We start out going very fast in the negative direction, but then we slow down, right? We're approaching that stoplight. Acceleration wants us to go in the other direction, but we're already going fast, so we just slow down. So acceleration is positive in this case. It's pulling you this way. But again, don't think about acceleration as a pull, because it's not a force. It's related to force, but it's not a force. So that's question 2. Here's question 3. Describe the velocity and acceleration for each section of the velocity time graph. So this is a good graph question. I'll give a moment to think about it. Need to hydrate again. All right. So let's see what's going on here. We have a velocity versus time graph, and let's just scroll back because I think this is super important. So we're looking at this second row here, and the slope gives us acceleration, and the area under the curve gives us displacement. Sorry, were we looking at a velocity versus time graph? Yeah, we were. Okay. So we want to describe the velocity and acceleration. So we don't need to look at the area under the curve. That gives us displacement. We only care about velocity and acceleration. So velocity we tell from the graph directly. Acceleration we tell from the slope. So let me just write that down. Velocity direct. Acceleration is slope. So let's take a look at A. Well, what's going on with the velocity? Here the velocity is 0, and we'll just assume that this is like a normal axis, so the top part is positive values of velocity and the bottom part is negative. So in A, the velocity is positive. Why? Well, because if we look at the graph, section A is in the positive section, right? It makes sense. But as we travel along A, at this point here, the velocity could be like 1. But at the final point of A, the velocity isn't 1 anymore. Now it might be like 5. So while we're in A, the velocity is positive and the object is speeding up. Right? So at like some initial time, it has just a velocity of 1, but as time gets a little bit further along, it has a much larger velocity. It's traveling faster. So it's speeding up and it's moving in the positive direction. So positive direction. And what can we say about acceleration? Well, if we take a look at this line here, the slope is positive. Slope is positive, which tells us acceleration is positive. So that's a pretty good description of what's going on in A. B. Let's take a look at the acceleration first, because that's just taking a look at the slope of the line. Acceleration, well, the line is horizontal. What is the slope of a horizontal line? Well, that's rise over run. In this case, there is no rise, so the slope of a horizontal line is, well, 0. So it has no acceleration. Well, what does this tell us about its velocity? Well, at this t equals, let's just say that's t1. This is t0, and let's just take a look here. This is t2. At t1, we're traveling at 5 meters per second. At t2, we're traveling at 5 meters per second. At any time in between t1 and t2, we're traveling at 5 meters per second. That means we're traveling at a constant velocity, right? Constant, positive velocity. Why is it positive? Well, because we're in the positive side of the velocity versus time graph. It's still like perhaps 5 meters per second. That's just an arbitrary number that I just pulled out of nowhere. But we're in the positive section of the graph, and it's constant, and it should make sense because we saw earlier that when we have a constant velocity, the acceleration is 0 because there is no change in velocity, and that's what acceleration is measuring. Cool. Let's take a look at C. So C is just this section here, and I'll just mark this as T3. So at T2, the object has a velocity of like 5 meters per second. At some time in between T2 and T3, just this point here, maybe it has 3 meters per second. At T3, it has 0 meters per second. Its velocity is 0 meters per second. So at any point in C, except for T3, the velocity is still positive. We're still above that x-axis. So velocity is positive. Acceleration, well, let's take a look at this line here. If we take a look at the slope, it's a negative slope. You know, it's pointing in that negative direction. So acceleration is negative. What does this mean conceptually? Well, if we started out at 5 meters per second, and at T3 we're at 0 meters per second, we can think about like the object slowing down. It started out at this 5 meters per second, and then it reached 0 meters per second. Slowing down, acceleration's in the negative direction, and we can start to see a pattern that like when the velocity and acceleration signs are opposite, then like the object tends to like slow down and perhaps eventually stop. Alright, so that's C. Let's move on to D. Now we enter the bottom section of the graph. So this means the velocity is negative. What about the acceleration? Well, we just take the slope of the line, and it's negative. And again, we'll pause just to consider what's happening conceptually. So at T3, we said the velocity equals 0, and let's just say that this is T4, and let's just say this is negative 5 meters per second, right? So I'm gonna draw out some sort of like positive direction. We have some line here and a negative direction. So we have some object that started out from rest. And let's take a look at what happened when it reached A. It started to speed up, and eventually it was at 5 meters per second at point A, right? And then at B, it traveled with a constant velocity. So those arrows are supposed to be equal. So this is A, that's B, right? Then when we go to C, it has that high acceleration. Sorry, it has that high velocity. I'm just gonna make these lines a little bit longer. This is the positive direction still. But at T3, it eventually comes to a stop, 0 meters per second. So the object starts to slow down. The vectors get a little bit smaller. So we're here at C, where it temporarily stops. Now D, it starts at 0 meters per second, but at like some point in between T3 and T4, maybe we're at negative 3 meters per second. So the magnitude of the velocity is increasing, 0 to 3 to 5, but it's a negative, so it's just pointing in the negative direction. So let me just change colors so we can really see this. What color do I like? Let's do blue. So it goes like -1 meters per second, -3 meters per second, -5 meters per second, and we're going in that negative direction, and we are accelerating in the negative direction. We're getting faster in that negative direction. The signs match, so we're going faster. We're not coming to that stop. So that's a really handy trick. If the signs match, we're probably getting faster. If the signs oppose each other, we're probably getting slower. Remember that. It'll help out a lot. E. Well, we're still in the negative section, so velocity should be negative. So that's pretty self-explanatory. Acceleration, that's slope. Horizontal line again, 0. No acceleration. And that just means we're traveling at that constant velocity again, similar how we were in B, except now just in the negative direction. So I'll just draw that. So now we're here. This is point D, and this is at the end of E, something like that. Lastly, we look at F. Velocity, we're still in the negative section, so it's still negative. We're still below the x-axis. Acceleration, we take a look at the slope of this line, and the slope is positive. So acceleration is positive. And so, well, what can we start to conclude? Velocity and acceleration have opposing signs, so we expect the object to be coming towards a halt. It should be slowing down, and that's exactly what's happening. At the start here at t5, we're at -5 meters per second. We're traveling very fast in the negative direction. But at t6 here, we're at a stop. We're at 0 meters per second. So if we see this visually, we're going fast in the negative direction, but we slow down to a stop, and we come to a stop here at F. So essentially what's happening on this journey, we're going in the positive direction. We start out accelerating, and then we maintain a speed, and then we deaccelerate, and then we just come back. From this endpoint, we turn around and we start accelerating back. We maintain a constant velocity, and then we come and slow down back to where we started from. So that's what the graph is essentially describing. Awesome. Let's move on to question 4. This should be the least complex problem thus far. It doesn't have any subparts, so I'm looking forward to this question. But then again, I created this presentation, so. Anyways, the graph above shows velocity v versus time t for an object in linear motion. Linear motion just means like the motion we're dealing with right now. One-dimensional motion, one-dimensional kinematics, stuff like that. Which of the following possible graph of position x versus time t for the object? Which of the following is? Okay, I misread that word. So, what do we know? We know slope of position versus time gives us velocity. So, of our answer choices, we should be looking for something that when we take the slope of it, we will get something that looks like the graph shown in the picture, right? So, for example, I'll just choose B to start out with. At the starting point, what color should I use? Let me use yellow. No, I don't want to use yellow. Let's use green. So at the starting point, and for most of the beginning, we're on this horizontal line here. So the slope here is 0. So in the velocity versus time graph, we should expect it to start out with a 0 velocity. And then for most of the middle part as well, there's no slope as well. The line is horizontal, so the velocity should be 0 here, and again here, v equals 0. So really, we expect the velocity versus time graph for this position versus time graph to be 0 basically everywhere, except for a couple of points. Just a couple of points. 1 second, let me just take care of this. Okay, anyways. So if we look at the graph, that's not what's going on whatsoever. We clearly have a velocity. It starts out positive, right? that's something to take away immediately. At the starting point, at t equals 0, the velocity is positive. So it's definitely not b, because there is no positive velocity in the first half. And then from there, we can sort of start to eliminate maybe some other choices. A, if we look at the beginning of this graph here, the slope of that is positive. It is a positive line, so maybe it is A. If we look at C, and we sort of, take a look at what's going on with the general trend of the position, that's a negative slope line. So the velocity would be negative in its graph, so it's not C either. And D, we see that, okay, maybe that is a positive slope, so now we're between A and D. So let's just look at the end then. At the end of this travel, the velocity is negative. So we would expect towards the end of the position versus time graph, the slope to be negative. So if we take a look at D, at the end, we're dealing with a positive slope, right? That's a positive line there. So that's not going to work, right? It's probably not D. And if we look at A, well, that's a negative slope there. So yeah, it looks like A is the correct answer. And that's what we'll go with. So let's take a little break first. There's a couple more problems. But hopefully everything's going well thus far. Yeah, I'm just going to take a little break for a moment. And, when we're doing so much physics, it can be exhausting. There's so much to learn and lots of concepts to go over. So, hopefully it's been enjoyable thus far. I've had a good time with this. There's just a couple more problems we need to get to. But I think these concepts are really important when it comes to physics. These establish the foundation of a lot of things we'll be going through down the road. So it's a really good idea to have a good grasp on these kinds of problems as well as the definitions. So let's get back into it. Short break. I probably should have had some water, but that's okay. Question 5. A car starts at rest and drives in a straight line at constant acceleration of 2 meters per second squared for a total of 100 meters. How much time is spent on the journey, and what is the final velocity of the car at 100 meters? Okay, so this is a very, very common kinematics question you'll see all of the time. This is the quintessential one-dimensional kinematics equation question. And I say equation question because we'll probably be using an equation. And for this, we sort of have to parse the question and really see what's going on, what kind of values are we given. So we see a car starts at rest. So this actually describes a velocity value. When we say it starts, we're talking about some initial time, and we're talking about velocity, and in fact, the initial velocity is 0 meters per second. The car is not moving, it's at rest. It drives in a straight line. That just means we're doing one-dimensional kinematics, nothing to worry about there. So when we learn more about kinematics, we'll see that this is important to take note of. By the way, kinematics just means the study of motion of an object. I probably should have defined that earlier on. Anyways, we're given that there's a constant acceleration of 2 meters per second squared. So A equals 2 meters per second squared. And it's important that we see constant here. For this class, we will be dealing with constant acceleration almost always. Though in Physics C, if you take that course, acceleration will change a little bit, and we'll have to use some calculus there. But for now, we have a constant acceleration value for a total of 100 meters. So this actually describes the change in position. And I'll describe that with a delta x. And that's equal to the x final minus x initial, and that's 100 meters, right? From the starting point to the ending point is 100 meters. They gave that to us, delta x. How much time is spent on the journey? So t equals question mark. So what do we have? We have v naught, we have a, and we have delta x. and we need t. So these are given, and we want t. T is want. So let's scroll back. Let's see, which equation could we possibly use? Well, this first equation, we don't have final velocity. We do have initial velocity. We do have acceleration. We don't have time. So we have two unknowns. We can't solve it. This second equation, we have this. This is delta x. So we have that. We have initial velocity. We don't have time. We're solving for time. We have acceleration, and we don't have time. So this equation we can use because we only have one unknown there, and that's time. So that looks good. And for this last equation, we don't have final velocity. We do have, sorry, I should have given an x here. We do have initial velocity. We do have acceleration, and we do have that. So we could use that. However, if we use that equation, we would be solving for final velocity, which is not what we want. We want time. So we need the second equation. So if we go back, let's use that equation. Let me change colors. I really like my colors. Let's do purple. A. So we'll use the equation delta x equals v naught t plus 1/2 at squared. See, I still don't remember my kinematics equations very well, so if you have these memorized, you won't hesitate like I do. So, from here we can isolate for t and just solve for it, or we can plug in the values that we have and just solve from t for there. Since this is a quadratic equation for t, we have a t squared term and a t term. It's not very fun to simplify it first, then plug in. It's just nicer if we plug in the values. So let's just go ahead and do that. So delta x is 100, and I'll write the units for it as well, though for now we'll be only concerned about the magnitude of the value, and then we can deal with units a little bit later. So that equals, v initial is 0 meters per second times t plus 1/2 acceleration we're given is 2 meters per second squared times t squared. So this we can simplify. I'll just get rid of the units for now because it's not super important. 100 equals, well, this just goes to 0, so 0 plus, this is 1/2 times 2, that's 1 times t squared, so this goes down to 100 equals t squared, which means that t equals plus or minus 10, but we're dealing with time, so the units is seconds, but between positive 10 seconds and negative 10 seconds, we won't get into the theory behind negative time, but that is a debate for a completely different time. No pun intended, but kind of. In general, we will be dealing with positive time, you know. The time spent on the journey was positive 10 seconds. Negative time is kind of used as like a comparison point. That's besides the point. So the answer here is 10 seconds. And you can play around with the units in this equation here, multiply it out, and you'll see how the units cancel each other out. B, we're looking for the final velocity. Final velocity equals what? Well, if we scroll back, we should remember that this equation right here, we had all of the knowns except for final velocity. So we can use that equation. And let's do that. So the equation is vf squared equals v naught squared plus 2a delta x. And we have a, we have delta x, we have v naught, we can just solve for vf squared. So we have vf squared equals 0 squared, 0 meters per second, plus 2 times 2 meters per second squared, I'll throw in the units now, times 100 meters. That's the displacement from up here. So let's solve this. Vf squared equals 0 plus, this is 4 times 100, and this just comes out to be 400. So we have Vf squared equals 400, and then that means that Vf is the square root of 400, which is equal to plus or minus 20 meters per second. And now it's an important question. We do have to consider, is it positive 20 meters per second? Is it negative 20 meters per second? Because that defines direction. So we don't actually know. The question isn't specific enough. It doesn't tell us what the direction is. So we can say that it is just 20 meters per second in, to say, some direction. In some direction towards final location. So that would be our answer there. If we had a direction, say that like it started here and then it went in this straight line and this is the positive direction, then we would say the answer is 20 meters per second. But I was not good and I did not specify direction in the problem. So let's move on to question 6. Just a couple more questions left. This is one of my favorites. If I drop a 0.25 kilogram biscuit from the top of the Empire State Building from rest, will it actually hurt someone? So let's find that out. And this is an age-old question, right? Like if you drop a penny from the Empire State Building or some really tall building, what would happen? We're just using a biscuit because why not? So yeah, we're gonna figure that out. Like what this part A is asking, what is the velocity of the biscuit just before it hits the ground? So let's do that. We'll start out with A. So we're given the mass of the biscuit. This is mass, which we haven't really talked about, so maybe it won't be that important. And it's dropped from rest, so V initial is 0 meters per second. And we're given that the Empire State Building is 381 meters tall. So that seems like some sort of displacement value. But let's just draw a picture. So this is my wonderful Empire State Building. And we're given that it's 381 meters tall. So the biscuit starts at the top and it goes down. So in this case, we're actually dealing with the y direction. The biscuit's actually in free fall. So that means we're dealing with gravity. So 381 is indeed a measure of displacement, except this time, instead of saying delta x, we're dealing with delta y because it's in the y direction. So delta y equals 381 meters per second. Cool. Now, before we proceed any further, we should probably, it would be wise to specify a direction. So let's let the bottom of the Empire State Building be the positive direction and the top be the negative direction. So the biscuit is traveling in the positive direction. Biscuit is traveling in positive direction. And I just chose those places arbitrarily, the directions. I chose them arbitrarily. You can flip-flop them, say that the positive direction is at the top, negative is at the bottom. It just, has to match the direction of motion. You wouldn't want to say this is the positive direction and this is the negative direction. That doesn't make any sense because that's not the direction of motion. Okay, so what does that tell us about acceleration? Well, we know acceleration, that's not the same color, too bad. Acceleration, objects in free fall, so it should be 9.8 meters per second squared of some form like that. So, I don't know. Is it positive? Is it negative? Well, let's take a look at the direction. It's pulling it towards the ground. That's what that's what acceleration due to gravity does. So in this case, the acceleration is positive 9.8 meters per second squared. So that's another quantity we're given. We're also given the initial velocity is 0 meters per second. And final velocity is what we're trying to solve for. So we have the initial, we have acceleration, we have delta y, we just need Vf. So if we go back to our equations, we can see that this third equation is the one that we need, except in the equation we're given delta x. We can just substitute that out with delta y, and the same sort of properties will hold. So if we use vf squared equals v naught squared plus 2a delta y, we can solve for delta y. And let's actually we can solve for vf squared, and it's already isolated, so we don't have to worry about isolating it. So vf squared equals v naught squared is 0 squared plus 2 times 9.8 times 381. So this tells us vf squared equals 0 plus, this is 19.6, that times 381. So this tells us vf squared equals whatever this product is, which happens to be 7471.6. And that means the final velocity is the square root of this, square root of 7471.6, which is equal to, I just needed some space, 86.43 meters per second. So how fast is that actually? I'm sure many of us aren't very familiar with like meters per second, so I'm just gonna go to Google on a different tab, and let's figure it out. So I'm plugging it into Google. 86.43 is 193 miles per hour. So that's a, dare I say, lethal biscuit. I think that can cause some damage. So now we know. Anyways, let's move on to part B. And this is saying, what is the final velocity if the biscuit has an initial velocity of 2 meters per second? So it's essentially the same question, except now v naught equals 2 meters per second. So we can just use the same equation because it's the same variables, and we'll just solve for vf again. So vf squared equals v naught squared plus 2a delta y, and that equals, this time it's 2 squared plus 2 times 9.8 times 381. And when we compute that, that gives us 7475.6. So we have VF is the square root of 7475.6. And that gives us, what does that give us? Let me check. That gives us 86.43 meters per second. Just kidding. It does give us that. This first answer should be 86.41, so that's my bad. And this is 86.43. So we can see that even if we apply some sort of initial velocity to it, 2 meters per second, that's in empirical units, that's like 6 feet per second, 6.5 feet per second. That's pretty fast. But its final velocity, right before it hits the ground at 381 meters away, it doesn't really matter too much whether or not we give it an initial velocity of 2 meters per second. That 2 meters per second is so little in the long run, so it's still a pretty lethal biscuit. C is asking, what's the final velocity if we drop the biscuit from the world's tallest building, the Burj Khalifa, which is 828 meters tall. And for this, we'll just assume that it starts from rest. So yeah, 828 meters is substantially taller than 381. And I think they're planning to construct a new tallest building in the world, also in like Abu Dhabi. I could be wrong about that, but I thought I heard something about that. But yeah, that should be pretty exciting. I've always wanted to see the Burj Khalifa, but maybe someday. Anyways, so we're solving for the final velocity again. And again, we have all of the quantities. We have initial velocity, 0 from rest. Acceleration, same, 9.8. Delta y this time is 828. So now we have delta y equals 828. But we'll essentially do the same thing. Vf squared equals v naught squared plus 2a delta y. So Vf squared equals 0 squared plus 2 times 9.8 times 828. And if we simplify this, Vf squared equals, what does that give us? 16228.8. And that means Vf is the square root of 16228.8. And we're taking the positive square root since we define the positive direction to be downwards. And that is 127.39 meters per second. 127.39 meters per second. Let's convert that to miles per hour really quickly. And that gives us 285 miles per hour. That's insane. What's the speed of sound? Speed of sound is 343 meters per second. So we're more than 1/3 the speed of sound if we drop a biscuit from the top of the Burj Khalifa. That's kind of scary to think about. Okay, question 7. This is a graph question, and it's multiple choice, so this one should be pretty quick. At time t equals 0, car X is traveling with speed v0, and it passes car Y, which is just starting to move. Both cars then travel on 2 parallel lines of the same straight road. The graphs of speed v versus time t for both cars are shown above. Which of the following is true at time t equals 20 seconds? So, if we look at the answer choices, A, B, and C, they all talk about the position of the cars in relation to each other. They're saying car Y's position is behind X's, or car Y is currently at the same place as X, it's passing it, or position of Y is ahead of X. So A, B, and C are all talking about position. D is talking about acceleration. So let's just take a look at acceleration quickly. Acceleration we know is the slope of velocity versus time. So if we look at car X, this has slope equal to 0 because it's a horizontal line, and this has slope as positive. So is 0 more faster? Is that bigger than a positive number? No, it's not, so it's not D. So now we have to really consider what's the position, right? Because that's what A, B, and C all have to do with. So we have to really consider displacement. And if we remember, for a velocity versus time graph, displacement is given by the area under the curve. And in this case, we're looking at t equals 20 seconds. So we're only looking up to this point here, the area under the curve. So for car X, the displacement is the area under the curve, as I've said so many times, and that is just the area of this rectangle here, right? It's this area here. So we can compute that geometrically, and that's just equal to 20 times v naught. Yeah, sometimes I like to do these fancy v's. It really just depends on the mood I'm in. But yeah, that's just the area under the curve. It's a rectangle of 20 times v naught. We don't have the value for v naught, but we can still use it as a point of comparison. For car Y, the area is, let's use a different color, let's use red. Now we're looking at this area, because it's bounded by this line here. So this is just the area of the triangle, and that happens to be 1/2 the base, times, which is 20, times the height, which is v naught. So that's equal to 10 v naught. So, based off of that, we know that 20 v naught is greater than 10 v naught, because v naught is greater than 0. Obviously, it's right there. And this should be quite self-explanatory, you're just multiplying it by a higher number. So what does that mean? That means the displacement of car X is more than the displacement of car Y, right? Because of this relationship here. And both cars were traveling with positive velocities, meaning that they were just going in one direction, and car X maintained a constant velocity, car Y was speeding up, but there was no point in which they turned around or anything like that. They were just going in the same straight road. So, if X experienced more displacement than Y did, that means Y is behind car X. So our answer is A. 8 is another graph question. Which of the following sets of graphs might be this corresponding graphs of position, velocity, and acceleration versus time for a moving particle? This should be pretty simple. We know that velocity is the slope of position, acceleration is the slope of velocity. So let's look at A. We are given a position versus time graph. It has a constant positive slope because it's a straight line. So straight lines are of the form mx plus b, and slope equals m, which is constant, and we see that the velocity is constant, right? So that makes sense. But then we come to acceleration. Acceleration is the slope of velocity. What's the slope of velocity? It's 0. There's no rise. So A is incorrect. That's just not right. B is a similar thing. We have this constant slope there, and this time the slope is negative, right? And that's shown very well here. It's the velocity is constant, and it's a constant negative value. So we feel good about that. Acceleration is where things go wrong again, because the slope of the velocity versus time graph is 0, and that's not depicted in the acceleration versus time graph. So B is wrong. C is where things get a little bit more exciting. Let's take a look at the velocity versus time graph first, because this first graph is kind of chaotic. So we have a constant slope for the velocity versus time graph because it's linear, and the slope is negative, and that is depicted in the acceleration versus time graph. So we feel good about the bottom two. Let's just compare the second graph to the first graph. So initially, when we start out, the slope at this initial point, it's something like that, right? It's a very high positive value. And then towards the end, it narrows out towards 0. So we would expect the velocity to decrease. It starts out at a high value and then it goes towards 0, which is exactly what's shown in this picture here. It starts out high and slow. So I feel pretty good about C. Let's just check D quickly. And we can see immediately that it's wrong. The velocity, the slope is changing throughout the graph, but it shows acceleration is constant, so it's not right. C is our answer. And that brings us to the last question of the night. So yeah, let's get it done, and we'll have a good night, and see you on the next week. But first, let's finish this question. And it's another graph question. These questions are so common to see graph questions. The accompanying graph describes the motion of a toy car across the floor for 10 seconds. What is the acceleration of the toy car at t equals 4 seconds? Well, we're given velocity, we're given time, so acceleration equals slope, and we're looking at t equals 4, so it's just the slope at that point. And well, we can just look at this line here and find the slope. So let's use two endpoints here. Let's use those 2 points. So the first point is 5, 1, and the second one is 3, -1. So, slope, that equals y2 minus y1 over x2 minus x1. So this is -1 minus 1 over 3 minus 5. That equals -2 over -2. That equals 1. So we expect the acceleration to be 1, and we have choice C here, 1 meters per second squared. So we'll choose that. We think that's the acceleration because it's the slope. And then finally, what is the total displacement of the toy car for the entire 10-second interval shown? Well, displacement equals area under velocity versus time graph. So we can do this geometrically by taking the sum of two separate areas. I'll use green again. Oh, that's a bad line. So if we take this bottom trapezoid and call that area 1, and this is area 2, then we can just say that, well, if we sum up A1 and A2, then we get the displacement. So, well, what is A1? The area of the trapezoid, area of trapezoid equals 1/2 B1 plus B2 times the height, where B1 and B2 are the bases of the trapezoid. So A1 is 1/2 times, this is length 1, plus this top one here is of length 4, times the height, which happens to be 1, plus, well, we have to compute the second area now. So this is 1/2. The first base is this top one here. Actually, it doesn't matter the order, but that top one is 3, plus this bottom one goes from 4 to 10, so 10 minus 4 is 6. So that's the second base. And the height in this case is that, which is 2. And if we simplify this further, we get 1/2 times 5 times 1, plus 1/2 times 9 times 2. So this gives us 2.5 plus 9, and that equals 11.5, which is not one of the answers, so I must have done something incorrect. What did I do incorrect? Well, one really big mistake. That is, we can sum the areas. We can definitely do that. However, we have to be careful about the sign of the area. And I know I said sign is very important when it comes to vectors, but it's also important when we're counting area. This area is below the x-axis. So it's actually a negative area, which sounds really weird. How do you have a negative area? If you take the area of a square, it's always positive. How do you have a negative area? Just trust me on this. It's below the x-axis, so it's negative. So technically, what we have to do here is, this is a negative 0.25. This is negative. And when we do that, we get that this is now equal to 9 minus 2.5, which is equal to 6.5 meters. And that is our answer. And that concludes the first presentation for AP Physics 1 in kinematics in 1 dimension. So hopefully that content was helpful. We spent quite a bit of time on lecture review and then some good practice problems in there as well. If there are any questions, feel free to comment them below. Like I said, this video will hopefully be up on YouTube relatively soon. And if you're seeing this on YouTube, feel free to come into the Twitch stream. Just a reminder of the schedule again. We will be doing the second AP Physics 1 lesson next week on Monday at the same time, 9 p.m. Eastern. However, in 2 days from now, Wednesday, which will be September 15th, will be the first calculus stream. And on Thursday, September 16th, we will have the first Physics C lesson. And as always, those streams will be weekly. And yes, so hopefully this was helpful. That concludes the first stream. I had a good time with this. And yeah, hope to see people in the future attending these Twitch streams live so I can help answer your questions that you have in real time and make the experience pleasurable for you. So with that said, that's going to do it for today, and thanks for tuning in.